Okay, test, test. Okay. Okay, I think all of you can hear me. Good evening to everybody. Today we'll do the the lab for word embeddings. So if you have the information for the links, you can follow. So meaning that if you have the options for the notebook as well as the files, you can download it off Canvas. But if you don't have, it's okay. I send you in the chat. I put the links. Uh, there's something wrong with Kaggle's uploading. That's why I didn't upload this exact copy. But this exact copy you will see it after I managed to update it lah. Okay, so I think my Jupyter notebook is too long lah. That's why you can't see what I'm seeing exactly. But I'll send you this walkthrough as well lah. Okay, so at the same time, you can prepare your data set. So if you are going to use Kaggle, then we're going to be use quite a few data sets. We're not going to use all of this. More than half of this we will use. But just for your sake, I summarized it in this file here, which is the https.com datasets here. You click on this, you can download and upload it yourself. The first link cannot access. Okay, let me check. Yeah, I think because it's a bit buggy. Okay, let me try it. Okay, let me try to fix it. Okay. Okay, should be fine already. Don't know if I need to edit it. Yeah, looks the same. Okay, thanks, Chikop, for your feedback. That is very helpful. I also don't know why Kaggle changed it to private. It was public, for sure. Some bugs lah. Okay, so if you click on the Kaggle dataset, okay, maybe I zoom in a bit in case it's hard to see. If it's hard to see, just bear with me. Uh, so the first data set is the data sets that you need to access lah. Okay, wait, sorry, let me check. Wi-Fi is a bit laggy. Okay, first data set is the data sets that you can access lah. So from here you should see a bunch of data like this. If these are all in your Canvas modules tab as well. But if you want to download these, you can. So I think if you click download, yeah, if you click download all. I think there's a download all button. Yeah, I think there's somewhere lah. I can't remember lah. There's a download button lah. If not, maybe you need to. There's one download button here. Or here, you can use this download. I think this will download all the files. So you download all these files and upload it to Kaggle first lah. So if you forget how to upload to Kaggle, let me do a short refresher. Uh, to Kaggle. Okay, so more people are here. Let me repaste the link again. Repaste the link in the chat again. So how you upload is you upload upload and then you click new data set, just drag and drop the files and upload it to the notebook. Okay, so that's just some admin. Okay. Okay, so for today, we'll be doing two things that are a bit more uh how do I put it? It may not be the most exciting in terms of developing applied AI models, lah. But in actual fact, you will be able to know more tools about natural language processing, as well as know more tools about how to do, for lack of a better way, vectorizing. Okay, so for today, there'll be two parts for today. The first part will be on tokenizing and processing of matrices. If you remember your linear algebra, your matrices, matrix, your matrix, then there'll be a bit about that. So just bear with me because it's quite mathematical. At the same time, sometimes I may stumble along and say the wrong thing about the indexes because there are so many different kinds of indexes to mention. Okay, so before the break, maybe you have a break about 7:40, 7:45, and then we'll do the word embeddings lah. If I'm not wrong, one of your TMA is on word embeddings. Yeah, but this one is slightly optional, but it's still recommended because even if you import pre-trained models, like pre-trained generative AI models, you also need to you also need to be able to uh, tokenize before you put into the AI model lah. Okay, so see some more people maybe have come. I'll send the link one more time, but you can access all of this on Kaggle lah. So that is not an issue. Okay, so the first part for today before the break, the tokenizing and processing of matrices may be a bit heavy lah on the matrix calculation side. So just bear with it. This updated notebook, if I send to you, you can revise and you can comment out the print statements, and it should be easier for you to understand the Python code. If not, just try to follow with the flow lah. It's gonna be a bit complex. Second one is the word embeddings, which is remember I'll give you some refresher later lah. But your word embeddings is the other two other than the n-grams that you have to use lah. So word embeddings will be quite Python heavy. So if you get lost halfway, don't worry. I think around next week, next Monday, I will update this notebook, and you can check it out again. Okay, so without further ado, 7:05. Yeah, let me copy this references one last time. Okay, and then see if you can access. Okay, so today we'll go through the optional methods for tokenizing. So optional, I think, is because it's not tested in a practical sense for your module. That's why I think it's optional per se. But there's also something, as I said, whenever you put data into an AI model or a natural language processing model or a generative AI model, a large language model, you need to do tokenization. But most of the pre-processing actually, most models will handle that. But we'll go through the processing of it for today. Okay, so I'm going to be using the data set that I said you can download from the links that I sent. If not, you can find it in the modules tab in your Canvas for your ICT 302 lah. Okay, so today we'll go through tokenization. Okay, let me find an optimal way. Okay, maybe I close this, zoom in. Let me find an optimal point to zoom in. Okay. So, if you remember tokenizers, if you don't know the definition, then tokenizers is something, okay, in this case, is from tokenizers import tokenizer. So you are importing some form of tokenizer lah. So in computer science, a lot of people like to share their libraries. So you can build your own tokenizer, as I showed last week. You can just do split. You can just do string split, can split however way you want. But today we'll show you a library for tokenization. So if you cannot access tokenizer, then maybe you'll need to do pip install first lah. So you should be familiar with the pip install and how to do pip install. So for the tokenizer, we will import one kind of model. Okay, so in the stricter sense, a model is something that does some form of prediction lah, or some form of sort of a function that brings out a number at the end of it. So meaning like equation y equals to x, y equals to mx. M is sort of like the model. Y equals to mx. M is the model lah. So for example, y equals to 2x. If x equals to 1, y equals to 2, right? So 2 times 1. If x equals to 2, y equals to 4. And then that is also some form of modeling lah. So a model is like you're trying to get an output from some form of equation lah. Okay, or in AI sense, it's some form of non-deterministic way. So today we'll go through some byte pair encoding tokenizer lah. Okay, and then some tokenizer tools that you may not need to know is sometimes as the name suggests, is a white space for checking for white space, and then tokenizer to train lah. So BPE stands for byte pair encoding. Byte pair encoding is just a subword tokenizer, which I realized I didn't explain what the token means again. So for example, token is, for example, if you have a sentence like this, you can break this up into a token such as hello, comma, my, comma, name. Okay, so this is one way to break it up into a token. The other way to break out a token, which I think last week, I think last week's lab and your, as well as part of your TMA, is also to figure out how tokens, maybe there's another way to do tokenization lah. So I think I can't remember if it's this lab, this practical, but sometimes the token can be split according to like that. Uh, Yeah. Sometimes also lah. But then this is really based on how the model, if you're using a tokenizer that is like a model, it will make a decision of how to split for you lah. So a BPA will make the decision on how to split for you, the tokens lah. Okay. So syntax wise, sometimes it's just most students will ask how come the Python code is written in this way and that way. So a lot of time, the response that I will always give is, this is the syntax of how the people that design tokenizer, that's how they decided to build it, lah. And there's no other way to put it, as in they are the ones that develop the functions. If you develop a function and you deploy it in the Python library, you wrote it in a certain way. So these people wrote it in a certain way, lah. There's not really any way for me to justify why is it written in specific ways, lah. Okay. So for example, tokenizer, in this case, the tokenizer, you want to pair it with the BPE, lah, so the byte pair encodings. BPE is some form of tokenizer, lah, okay? So sometimes if you want to know what a class is when you're using it, either you read the documentation or you can do print statements, lah. Okay, so in this case, when I print the BPE, what is BPE? If I print a bracket BPE, yeah, you see, for example, BPE, they'll show you what is the parameters now. So, as I'm looking at it, it looks like there's some form of modeling that goes on it, lah. So dropout is some form of, you may not know it, but neural networks is some form of parameter to tune, etc., etc. Okay, maybe I not don't bore you on that, lah. Okay, and then the next one is after I define the tokenizer, what are the variables? So the variables of tokenizer is there are a lot of these words, lah. You may not know them now. We're not going through, but this is a tool that has different kinds of terms here, which I will not confuse you lah. But these are the terms that you will see a lot when you're doing tokenization, if not training large language models. Okay, so after that, there's also other things to define, like the pre-tokenizer is the white space. So for example, tokenizer dot pre-tokenizer, there should be a pre-tokenizer here. So I print the tokenizer here, right? So this is the printing of the tokenizer here. Pre-tokenizer set as white space lah. So pre-tokenizer is in case you want to predict any white spaces lah. Yeah. Okay. And then when I print what are the variables of a BP trainer, then you can see what are the BP trainer. You can see this, there's some, it looks like some form of training lah. So minimum frequency, vocab size. Okay. So I don't bore you lah. It's just some way, some syntax that you just need to briefly read. You don't, if you really need to know, you print it out. If not, you search what is BP trainer or documentation wise lah. Okay. So for example, the BPE trainer, think of it as BPE is the tokenizer lah. You want to split the sentence into words now, right? Because we're doing a natural language processing. We split the sentence into words. So in this case, BPE trainer, you are assigning it to the first element, which is U and K. So when you see U and K, it tends to be the term unknown. So there'll be a lot of unknown. Yeah. And then at the same time, there's this thing that's similar to a context window that's known as vocabulary size. There's how many, in the case if vocabulary size is words, how many unique words that the trainer can memorize, if not contain. Okay, so most likely this trainer will be able to remember unique words of 1,000, and once it exceeds beyond 1,000, it will sort of either forget it. Yeah, so it's quite similar to the context windows of generative AI tools. You will realize in the beginning, I think, Copilot, no, sorry, Microsoft Copilot, after you reach like 20 prompts in the chat, then they say, oh, you need to start a new chat. That's because their context window is smaller. Okay. So right now, what's happening is that you want to train the model with the file of this Kaggle notebook file, and you want to define it as trainer lah. Okay, so this Kaggle notebook, so this Kaggle data set, if you want to access it after you uploaded it, just a short refresher. I'm looking for the TED 2013. Okay, 2013. That's TED 2013. Then, for example, here, if I just wanted to integrate it, I will click on the copy and then I will paste it. So if I paste it just to show you, then this is where my data set is now. Okay, so just to show you what the data set is, I double click. Then it's a bit small, but what you can see is, let me close it a bit. Okay, so what you can see is that this is a TED 2013 talk. Yeah, for token. Okay, so I see a question. Yeah, so one question says for tokenizing, how do we decide whether to use manually lab one or via the library shown today? Uh, so so I think the question in the TMA, you may correct me if I'm wrong, but the question in your TMA will tell you which tokenizer to use. If not, you can just choose one. So the question in your TMA will ask you to use the tokenizer from uh uh the tokenizer. Okay, today quite long. They'll ask you to use the tick token tokenizer. So this one is the tokenizer that you have to use. Okay, so thanks for that question. Okay, thanks for that question. Yeah. So later we'll go through the tokenizer. Okay, so besides that, sorry, I should have closed the file. So just that you see lah, the reason why I'm showing you is because you will realize that some of the files later you will get utterly confused what these files are. But I just showing you this is like normal text lah. So in mid 16th century, blah 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 blah. This is just normal text lah. Okay, so it's a text that you understand lah. It's not like weird words ah. Okay. Okay, so just think of it as the tokenizer takes in this file and it starts to decide what is the best way to tokenize it lah. But it's following the how the trainer is training it lah. So you can think about it as when you're using AI models, you want to train them as well lah. Okay, so wait, there are 13 people and I think it will stabilize at 13. So I will just copy and paste in the chat again one more time the data for today. So in this case, so the trainer is BPE lah. So if you do a lot of AI, if you do a lot of development in AI, you will realize that there are a lot of models for you to choose from to train different things lah. So one part of the AI skill set is just trying different models lah. So in this case, a BPE trainer is just the model here lah. So in terms of that, like what the trainer is that if you just for me very succinctly to explain is that if you want to train an AI to do if you want an AI to do a specific task, you have to train it lah. So in the case of if a good example is that if you have a phone, right, you want it to unlock your face with it. So I'm sure you use your face and unlock your phone. They will ask you to like take a few pictures of like left, right, up, down. So they're taking multiple pictures and then these pictures are being trained on a specific model in your phone. So once it is trained on your face, it should recognize your face quite well. Okay, so same as I think SingPass was doing that, like did that quite recently, right? They make you scan your face. Yeah, make you scan your face. Yeah, but besides that, so same. The problem set may not be so interesting here, but in the event you are supposed to think of a way how to split the words, and then you can figure out what is the best model that has already been trained to work on this data set. So it's using this data set and it's learning the patterns of the data set to split it up. Okay. Okay, so in this case, if you have done a bit of AI before, then you do some form of setting, right? Then after the setting, you will do some form of training. So if you use sklearn, scikit-learn, is normally dot predict. If you use neural networks, I believe, it's been a while. It's dot train, I think. I can't remember. Wow, it's been a while. Normally I read more code than I write code. So encode is you want to do a prediction in this corpus of text. So corpus is the short form for just a bunch of text. So in this case, see the output of the encoder. This is the output of the encoder. So you see this corpus is from TED Talk 2013. But then the output is okay, can I zoom in a bit more? This output is this core P us is from TED Talk 2013 2002 I mean 2013 then dot lah. So you ask me why is it like that? The truth is that's just how the BPE trainer the byte pair encoding has decided to do this form of tokenization. So sometimes not most things are explainable, but let me see if I think there's a link here for me to explain. Okay. So you can see some definition of what BPE is. BPE is an iterative algorithm that starts with individual characters and builds up by full words by merging. Okay. So there's a lot of words here. But maybe we just read this line here. This creates a subword vocabulary where common words like is stays whole. So is here, right? So corpus is like is stay whole. So what it's saying is that the BP algorithm is using very, very common tokens lah. So is a token, core is a token, p is a token, us is a token lah. Okay, so it's just doing that lah. Okay, then I found this visualizer link that maybe can help you understand better lah. Okay, so maybe I use this sentence. This is a sentence. The space quick space brown fox jumps over the lazy dog. Okay, so I can show you the token IDs lah. The token IDs lah. Okay, so the trainer has sort of already decided which token has which ID lah in a certain place lah. So it's been trained that way to decide. Okay, so we can see, for example, steps. We can see, yeah, let me see if the animation plays well. Okay. So step one, it will, all the words will be individual characters lah. And then you see algorithm will try to merge the words together and see if it makes sense lah. So honestly, the way that it merges is some form of statistical method lah, some form of math method lah. So it's just going to merge things and see what is the most common word. Okay, this is a very bad example. I realize is that the crypt brown fox is a very common word being used. Okay, it's not merging. Okay. Can I play? Oh yeah, stop merging. Oh, yeah. Okay. Never mind. I use machine learning instead. Okay, so machine learning. Okay. So if I run the BP algorithm lah, don't worry, okay, if you want to use it, I send you the link in the chat now. Okay. If you want to use it, I send you the link in the chat. So sorry, let me start from again. Let me start again. Okay. Start from the first step. Okay. Yeah. So sometimes it will just choose the word that either has the lowest ID or the most common word lah. It's variable lah. So you can see that it's just trying to split and to combine words that are most common lah. So just now the in was split first, and then now it's splitting according to machine and then learning and R. Okay, so but I won't belabor that lah because I don't think you have an assessment that is testing your BPE. Yeah, so I will skip that, but you can access it if you want. Okay, so think about it still as some form of black box lah. That black box, sorry, if I need to explain what black box is that it's an algorithm that decides what's the best way to split the words in a sentence into its own tokens lah. So it just splits it like that. Okay, I think I labeled too much. Let me go back to the next thing. Okay, so you should already be familiar. Now, if I'm going to open the same text again, what I can do is that I can use this syntax lah. So from last week's lab, you should be quite familiar with open the TED Talk as file read lines lah. So I'm going to read the lines, and then what's happening is that I create a array that stores there's nothing, but is to store the token values lah. Okay, so with that, what is happening is that just now I just tokenized based on this corpus is from TED Talk 2013. So this corpus is from TED Talk 2013. This is the result. Okay, but right now I want to tokenize this whole data set. Right, so this one quite big, right? Just now, just a refresher. If you find that data set, I think TED is all the way below here. It's quite long lah. Okay, so now we're going to use the tokenizer on it. So it's going to read the lines first, and then it's going to read the lines, and then for each line, it's going to do the encode. So remember, encode is like the predict lah. So it's going to encode each line. Okay. Let's see. Should I do a demo? Okay lah, don't need demo lah. I think you'll understand. Is that for line in lines lah. So just now that TED Talk, every line you will split into tokens, and then you can see the result. I just print the top three elements lah, or top four elements lah, which is in the mid dash 16th century. It now also quite confusing. It all is okay. I can't read it also. Yeah, but you can see that it just decides how to split it lah. So it's still using the BPE to split it lah. Okay, so that is just a long way of me explaining it. Okay, so to just give you the understanding about what is this process that just happened. First we did the training, which is building the BPE building the dictionary lah, which is using the BPE trainer lah. So the BPE trainer acts like a scientist and it looks at all the text and it doesn't decide the meaning of the sentences, but it looks for patterns to split lah. Yeah. So in this case, it's just trying to split the data lah. But then what's happening now is that after it's being trained on the corpus of text, which is the TED Talk, now you want to do inference or encoding, which is you want to split up into tokens and you want to see how well it does lah. So I think I forgot to mention, sorry, is that every time you use AI to do certain solutions or use modeling to do certain solutions, you must always think of the pros and cons lah. Just because you apply AI model to it doesn't mean that it will give you the answer all the time lah. Okay, so not that it's hallucination, but it's something that you must think about lah. You must use your brain to evaluate whether AI model is doing well or not, and this should be something you're familiar with at work lah. You should be familiar with it. Should be familiar with it as well lah. When people give you work, if you're a manager, people give you work, or you give your boss work, they also critique it lah. So they use critical thinking skills lah. So inference and encoding is that the BP encoder will decide how to split the words lah and translate them into the different pieces lah. Okay. So the output, example, the output is the corpus, like the CORPUS. Okay. So don't really need to know what the BPA and how it does it. This is not the time for it, but it's just for you to take note lah. Okay, so besides that, how do you apply this train token to any text lah? So in this case, there's a text here from the SUSS website. So what makes SUSS unique? And then if I take this text and I apply it to here, okay, if I apply it to here and then I just paste the text lah, how will you do the tokenization on it, right? So you already trained the model and then you train the BPE model to tokenize words using the TED Talk, right? What you can do is that you can retrain the BPE model to uh, predict the patterns from this text, or you can just use the BPE model that you have already done, and then you split up this text. Okay, so because I think we don't have a lot of time, let me continue. So what should be done is that you just simply put the dot encode now. So when you encode, then for example here the dot encode is like the predict, you put your text inside, and then if you want to get the tokens, then what makes, yeah, so you can see this prediction may not be the best lah. So it's like what MX SUSS unique. Okay, so this is one of the results. Okay, don't worry if you don't have this, I will send this. I will save it in Kaggle or send you the notebook. I'll put the notebook link in the announcements tab that you can access also. Okay, so simply put it, just remember tokenization, just encoding or prediction will be fine. Okay. Okay, so another refresher, but also something that you'll see that was from last week. Not last week, sorry, 2 weeks ago, is that from collections you import counter. So what is a counter? A counter is going to count something lah. In this case, you're going to count the vocabulary words lah. So for each line in the tokenized corpus, you want to update each line. Okay, so let's see. So for example, if I do a print statement here. Okay, so I realized I didn't show this the last time, but next time if you want to run Python code in the same line, just put a semicolon. Okay, so what's happening is that for each line in the tokenized corpus, which is tokenized corpus is this one. This is the tokenized corpus, right? The TED Talk. For each line in the TED Talk, you want to add it as a key. So a key, and then you want to add the value pair as well. You want to count it. Okay. So that's just to let you take note. So what this says is that IBLE appeared twice in the first line, because I did print vocab and then I broke it. Okay. And then if I let it run on its own, then it will just run through all the different lines of code. Oh, it's taking some time. All the different lines of code, and then you print up to 999 lines lah, because I think we set it to 1000 as the limit. Yeah. Okay, so this just counting the words lah. This one like not familiar, you're familiar lah. Okay, but now this is another way of counting. So maybe I zoom out a bit, so you can see. So for example, in the seminar also, the topic of co-occurrence matrix. So a co-occurrence matrix is a table that counts how things often appear together in context. So let me use this corpus of text, two sentences, I love AI and I love coding. Okay. So look at the output. So our output here is the co-occurrence matrix. So what do you think how do you think this output is formed? Okay. So you can see I love, I love appeared twice. So I and love appeared twice. And then love and AI appeared once only, right? Love and AI appeared once, love and AI appeared once. And then love coding appeared once, love coding appeared once. So current co-occurrence matrix is saying uh how do pairs of words exist with each other. So something like bigram, n-gram, but like a number two n-gram. Yeah, something like that. But this is a co-occurrence matrix. Okay. So the reason why I'm going through something so basic is because later the code will go above your head for sure. So just fly above your head. But uh, if you are needed to study, if not do this for your assessment, then come back to refer to it. Okay, so I'll give all this to you. I know the one in the canvas is not it's quite bare, but I'll give you this one to help you better understand as well. Okay, so for example, if we want to set up a co-occurrence matrix, we can use NumPy to create a two-dimensional array. Yeah, correct. Two-dimensional array lah. Okay, so what is a two-dimensional array? You should be familiar with NumPy if you've taken Python, right? Which is NP ones. What's NP ones? You're gonna make an array that is 1000 by 1000. Okay, so you can see that I print this, right? NP dot ones means that you create ones, and then it'll be 1000 rows and 1000 columns. 1000 rows, 1000 columns, or either way is also fine. Okay, I don't memorize the syntax normally. I just type to see how it works. Okay, so in case you have done a lot and remember your Python, if you do shape, then the shape will tell you it's 1000 by 1000 as well. So this is rows and columns. Okay. So, but it also tells you it's two dimension, meaning that there's there's X and Y. Yeah, so row and column. Then three dimension is X, Y, and Z. Okay, which means that we like comma 1000. Also possible. Oh, maybe I can do that also if I do this. Yeah. Oh, canvas. I mean, sorry. Kaggle is a bit slower. Yeah. So this is a 1000 by 1000 by 1000. Okay. But I should change the code back later because it may mess with the subsequent parts. Okay. So this 1000 columns. So 1000 rows by 1000 by 1000 and then by 1000 again. So you think of it as a cube with 1000. Easy if you don't know, it's like think of a cube as like 1000 cm by 1000 cm by 1000 cm. Same thing lah. Okay. So that's just to help you visualize. Okay. Besides that, I remind you of what the tokenized corpus is again. Okay. The BPE tokenized it to a very weird kind of way lah. Okay. Weird kind of way. So you can see this is quite weird. Doesn't look like words, but that's the tokenizer that we chose. It's not the perfect tokenizer, but it's something just to show you lah. Okay, so now we're gonna use this tokenizer and we're gonna create the co-occurrence matrix. Okay, we're gonna make the co-occurrence matrix. Okay, so let's see how that is done. So I'm gonna run this code first. So it's going to take some time. It's going to be a bit confusing. But for each line in the tokenized corpus, uh, when it runs through each line, it's going to do another for loop to loop through each individual element. So each individual element will have an index. So enumerate, I'll show you example later. So it will give you enumerate means that when you look through each element, I want to have an index as well. So if I look through in will be 0, I will be 0, token will be in, then the next for loop when it continues will be I will be 1, and then token will be so on and so forth. Yeah, and then the next part is that for j in the range of maximum of I minus 2, so meaning the previous word, the two words before, or the or no words before, as well as the minimum of the third words from the front, if not the end of the word lah. Okay, so this is quite confusing. So let me jump to explain to you in a more truncated form lah. Okay, so today there'll be a lot of code lah, but let me explain to you in a truncated form. Okay, so So you see the problem with explaining this is because it's hard to demonstrate lah. So for j in the range of max I minus 2, comma 0, max all this, right? So what is happening is that I will be the word index lah. So for example, in is here, and if you want to take two words behind, you can't. So that's why there's the max 0. And then the minimum here, the range will be plus 3, if not the length of the line lah. Which one is the minimum? Length of the line will be the whole line, right? Then the minimum is plus 3 only lah. So 1, 2, 3. So this will be here. But imagine if it's the range of the index at th, right? So th minus 2 is here. Uh, and then comma 0. So the max of that is here, right? The max of that is here. So think of it as the range starts from here, and then minimum I plus 3, 1, 2, 3. So the 3 is here. Mean of the length of the line is here, right? So what is the mean of the length of the line is here. So it's essentially doing a for loop to check uh these elements lah, here lah. Okay, so do a for loop to run through these elements lah. So you can see it's like a sliding window kind of thing. And then, for example, in the co-occurrence matrix, you're going to add these. You're going to add these tokens. You're going to add these values into the co-occurrence matrix lah. But you're going to use the tokenizers dictionary to do that lah. Okay, but that's confusing. But let me show you an example. Okay, so in the sense here, what happens is that if we already have a word tokenizer that breaks up the sentence, the quick brown fox jumps over the wall. For I in word enumerate, you can see the start, same thing, right? Start. We're taking either the element that is two numbers away, or the element that is at the start, okay? Or we can take the end, which is the plus 3, if not the full length of the sentence lah. So what is happening is that what you can see is that this is the output lah. So and then it's getting the next two words yeah, the quick brown, and then there'll be the quick brown. So, and then it's just the center word lah. So the center word will be the I, and then the words are surrounding it will be predicted as it lah. Okay. Okay. So somebody just came in, so let me paste. Let me see if I can pin it instead. Okay, let me copy, paste it one more time. Okay. Can. Okay. So after you do that, when you're doing the co-occurrence matrix, you're still using the tokenizer to search for the token ID, and then we search for the token ID with the token, then you put it in the tokenizer lah. But right now you're probably confused. This is the part that you have to run the code to understand. If not, it'd be quite tough lah. So, but you're just doing the same thing. You are trying to add the tokenizer into you try and add the word into the co-occurrence matrix lah. But the problem with that is that when you print a co-occurrence matrix, they are in numbers lah. So this is the tough part to explain, is that everything is just broken into numbers and it's tough to see lah. But co-occurrence matrix, as I refresh again, is something like this lah. So I love AI and I love coding. You tokenize these two sentences and you create it into creating a co-occurrence matrix. This is what you get lah. I love occurs twice, that's why it's 2. Yeah. So just to let you know lah. So but it will just convert it into word numbers instead lah. So that's where the word embedding concept comes about lah. You want to use numbers to represent instead of words. Okay. Okay. So we're going to push through a bit, but I realized that because time may be a bit short, and because we were told to say that a lot of the matrices are optional because you may not be tested on them. So I'll just go through some concepts in terms of I'll go through the concepts instead of the code, lah. Yeah, okay. So for example, the PMI matrix is a co-occurrence matrix that measures how surprisingly two words occur together lah, compared to chance lah. So there's a mathematical formula behind it that determines it lah, okay? So let me follow. You just need to stare at the formula, and then this formula is telling you that I'm going to do a log base 2 on the probability of x and y being together, the word x and word y being together, divided by the probability of x occurring and then y occurring now. So just based on this statistical formula, they will make another set of numbers, another matrix that hopefully will be better at predicting what is the next word occurrence lah. So that would be one use case lah. But I think so I won't go through the code for this part, but I will let's look a bit more at the more important one that you see quite often is this thing called the cosine similarity matrix lah. Okay, so I think under this also supposed to be optional per se lah. I think the code is optional lah. That's because we won't really have a lot to apply. I mean, we'll apply this, but I don't think you need to necessarily know how to the math to calculate lah. Usually you can just find a library that says cosine similarity, then just plug it in and then can already lah. Okay, so cosine similarity is something like this. It's basically for vectors lah. So in plain words, if you take the dot product of two word vectors, so for example, word vectors can look like these. They're like arrays lah, two-dimensional arrays, three-dimensional arrays, four-dimensional arrays. You do a dot product and you divide by their magnitude, you will get this thing called a similarity lah. So similarity will be a number lah. Okay. So let me show you a simple link to help illustrate that as well. Okay. So similarity cosine calculator. So you can see there are no words here in the graph. Let's choose a comparative word like monkeys, monkeys, and then I say find the most similar, find the most different. Okay, compare. Okay, so monkeys is here. Can see the term monkeys here lah. But what is the so cosine similarity is something like from a specific point, you may want to draw it towards another point lah. So from here you can see that if you have 2 points, what you can do is that you can calculate an angle and then you can draw a line with each of them, and then this distance is how similar or how far something is lah. So for example here, animals and monkeys is quite near each other lah. So animals and mammals, insects are quite near, but congress is very far away. So the similarity is like the distance lah. So the further the distance, the smaller the similarity in this case lah. Okay, so that is the case for similarity. Sorry, this case for similarity lah. Okay, so just long story short, because most of that is optional. So you can refer to what cosine similarity is as just a form of you converting the vectors that you want to use as distances lah. That's all lah. Okay, so for this part I won't label on it. So to just let you know lah, that there's a formula that does the cosine similarity lah. Okay. Okay, but ultimately, after you do all that similarity and very similar to this diagram that we are looking at, right? Not only do we want to look at just numbers for the sake of numbers, right? Because that may be quite useless. So for example, a car, we don't want to look at numbers for the sake of looking at numbers for no reason, right? But we want to see what the relationship between words lah, and they tend to be communicated with numbers, right? So distance is a way to communicate with numbers lah. Okay, so in the sense here, what is going to happen is that we can convert numbers back and forth, words back and forth based on their distances, right? So in this case here, as we're having the tokenizer, there is a function called dot token to ID. So dot token to ID is that once you have this token, you can track what the ID is inside the tokenizer lah. So inside the tokenizer, there's an ID that's being stored somewhere there. And then at the same time, you can find the similarity between the most similar dictionary of the dot ID, which is the dot ID here, as well yeah, the similarity score lah. And then what happens is, sorry, I'm abstracting most of it. I'm keeping it. I'm not explaining most of it because this is still optional. But then at the same time, then this similarity is that when you want to use this similarity to map within the same space of here with those numbers and words, because this also has its position, this number and words, then you can choose some form of most similar words lah. So when you want to check between the thought ID, what is the most similar, then thought, think, mean, love, this can be very similar lah. Okay. Okay, so there's a question asking, is cosine similarity calculated before modeling or after modeling to evaluate models? In this case, what we are doing is that we're just showing how to uh, yeah, we're just showing how cosine similarity is related to understanding the model lah. So the model is saying that these distances is getting the numbers of these distances lah. And then but in reality you have to check whether these models are well done or not lah. Okay, so I think that's not what you're asking, but I'm being a bit more verbose. Okay, so if I say most different, let me click most different, most similar, then you can see that, oh, okay, these animals and mammals, this model behind it is doing well because the numbers, the words that are quite similar to it are quite near. Lah. And then the words that are not so similar are actually quite far. So that is one way to evaluate whether the model is doing well. Lah. So cosine similarity can be done, in this case, is after modeling. Lah. It's done after modeling. Lah. If you want to do it before modeling, if you have not taken machine learning, that's hard to explain. But cosine similarity can be done as a scaling of your features, lah, which we will not. I don't think we'll cover for this module. But you are able to change the features before you put into the model. You can use some form of cosine similarity, if not statistical method, lah. Okay, so technically can be okay. What I'm also trying to say is that whatever statistical method that you see, like the cosine similarity, all this PMI lah, all this is there any more? No more. Just these, right? And later some more. Is that these are tools, these are mathematical tools lah that you apply, but you need to know whether you need to test it to see if it works. So in this case, whether it's before modeling or after modeling, you just test. You just need to apply the right tool. Okay. Okay. No, okay. Normally it's not the right tool. Just apply a tool to see if it works. But then you have to evaluate to see if it really works now. Okay. So it can be applied for both, but this case we are applying it after lah. We're applying it after. But in this case, yeah, in this case we're applying after lah. But that's because this model is not a real AI model lah, just a mathematical model lah. But yeah. Okay, so hopefully that helped you. So okay, I will gloss over the PMI thing. Just give me a while. Oh yeah. So actually, the point of learning all these things is that, in when you develop all these generative AI models, these are some of the tools now. So the co-occurrence are tools, PMI is a tool, the cosine similarity are tools for you to apply lah. So very good. It led up to the same conclusion as how I was doing the notebook as well. Okay, and then the last thing before I go on a break, I know it's more than 40 minutes. But the last thing, yeah, okay. Yeah. So yeah, to answer the question is you actually for AI engineers or data scientists, because the function is sorry, the person's question is that uh there are a lot of ways to do matrices, but how to apply them. Actually, most of the answers is that you will just experiment as many solutions to get the best model possible, or if not, the best way to evaluate lah. So I think that's not said very often, but all these are tools for you to apply. Sometimes it works, sometimes it doesn't lah. So you have to experiment lah. Yeah. So that's the short way of me saying it lah. So tuning AI models is an art more than a science sometimes, because the libraries are easy. The libraries are already done already, so you just need to experiment with different libraries lah. Okay. Okay, so visualizations, we will go through this part first, because it'll be a good segue to the end, to change topic after the break. So let me go through this first lah. Okay, so PCA, Principal Component Analysis, is something that is very common that you need to learn in machine learning. But I don't really have time to explain all of it, so I will just give you a semblance and an idea lah. Okay, so this original data set, and this is PCA lah. So what is happening is that you can see this two-dimensional plane becomes one-dimensional, left, right only. This is like top, left, right, up, down. So PCA, a principal component analysis, is an algorithm that helps you to, if you have many columns, to use the columns and digest it down to one or two columns with some form of math lah. Okay, so in this case, so this case here, for example, this case is this is two-dimensional, it becomes one-dimensional here. This two-dimensional is one-dimensional here. Uh, Another way to also show it is that, can I pause this? Cannot pause. Okay, cannot pause. Oh, laggy. Okay. For example, a three-dimensional can melt down or become a two-dimensional. So you ask me what is being done. It's a very complex form of matrices as well that converts three dimensions, two dimensions. So all the information of three dimensions hopefully gets retained to a two dimension. Okay, so in this case, let me close because everything is lagging, and I will not really go through the detail. Is that if you know how to use sklearn, then you use principal component analysis. You want to digest the data set from as many columns to just three components only, and you want to fit it inside. So this library is just made by somebody, so the syntax is just like that. Okay, so in this case, the co-occurrence matrix, right, is originally 1,000 by 1,000, which is 1,000 rows by 1,000 columns, right? But after you did the PCA fit transform, like you put it into the PCA model, right, throw it inside. Then after that, what happens is that these 1,000 columns uh, suddenly become three columns only. So there's an algorithm, there's a formula that runs on it so that it becomes the 1,000 columns. It uses 1,000 columns as evidence to reduce until three columns. This is actually what PCA is doing. But as I said, this is optional. That's why I'm not going through every single detail. Okay, so with that PCA, as we said, if there are three columns only, the way to visualize it is that you can visualize it in three-dimensional space. So in this case, this would be a sample of the three-dimensional space of the thought, think, first, next, head. Okay, or if you scroll down, another way to look at it is that this is three-dimensional. Okay, so that is the another way to look at it. Okay, so it's 7:50. Yeah, it's 7:50. So maybe let's take a 15 minutes break first. For a 15 minutes break. If you haven't uploaded all these data sets, you can upload these data sets and try it along as well. So let's take a 15 minutes break and we will come back after this because it's the next topic. And this is also part of your TMA as well. Okay, so take a 15 minutes break and we'll be back. 8:05. Okay, hopefully I'm back already. So okay, this is going to be the last maybe 40 minutes for today. But I guess this is the last thing that is relatively important so that I think part of your TMA, if not I think one of your questions for your TMA is that you need to use this tokenizer lah. Okay, let me remove this first. Okay. So how to import the tokenizer? Not no surprise, but import tick token lah. So tick token is some form of tokenizer. You can go and search online on the documentation. But just to let you know, tick token is also a BPE, a byte pair encoder. But is byte pair encoder that uses 50K tokens, I believe. So there will be an explanation of how this tokenizer works on the inside. Think of it as it's a black box, but just think of it as like this is a the tokenizer that works quite well, like, or in other words, it splits words up into good tokens. Sorry, it splits sentences up into good tokens, lah. So same as the logic. If you want to encode this whole tokens, and you can get the indices. So for example, the syntax would be take token, get encoding. You want to take the R50K base, the 50K base model lah. And then in the indices, you use encoding as you define here, and in dot encode, you predict it on so this tick token has already been trained. So it really has been trained. You're just applying it now, right? So the encoding at dot encode is that you want to encode these sentences based on tick token. So somehow the logic is that tick token gives you the indices first, which are the indexes of the words. So every word has an index according to the tokenizer lah. So in this case, if I print the index, you get 121, 318, 257, 1332, 6827, and index 0. And then if you put it together and you for each of the indices, you want to decode the token using the encoder. You want to decode the indices, what you'll get is that you'll get the words lah. So in this case, 1212, the index inside this tick token refers to this, which is sorry, this is a test sentence, right? So this is a test sentence, is how the tick token split it lah. You can see you can sort of do a if you use a split by space, right? You won't get this, right? You'll get this comma is comma a comma test comma sentence, right? Okay, we ignore the space lah, but you may not get the exclamation mark out lah. So basically, this tick token has some form of logic that it decides on how to split the sentence lah. So in this case, this is the way that it's done if you want to split the sentence, and exposure for you is that every word has index lah. So 2112 for tick token is this. 318 is 257 is it's not for you to memorize. It's just for you to understand that this is how the tokenization done, and they have the index and the words like not be confused. Okay, so another kind of refresher again is that if you look at the counter, you do the exact same thing. You read a different data set now instead. So this is the n tokens txt. Let me pull it out and let's look at it together. So n tokens.txt looks about the same as the looks about same as the TED Talk. Yeah. But just treat it as like another form of text lah. Okay, so another form of text. We're ingesting it, we are reading, and then we're splitting by the new line. So we're splitting into every new line. And then now we want to count the tokens lah. So tokens is however the tokenizer is going to split it, right? So for in this case, yeah, sorry, there's no tokenizer here, but in this case, what you're doing is that for each line in the text, you want to split based on the space lah. Okay, so if I just do this tokens, if I just do this, you will just get, oh, hopefully it doesn't lag. Okay, yeah, so in the mid, so it's splitting just by space lah. So in this case, the tokens is by space. And then I'll define another counter to count everything in the tokens. And then that's when I can have this syntax lah. Okay, so let's let it run. Kaggle a bit slow today. Yeah. So for example, the most common word, the most common is the length of the most common words is 25624. Okay. the most common few words lah. Okay, so if I do this instead, let me comment this out. Okay, it's running. It's running. So it's gonna print the top few most common lah. So in that case, the length of the top most common words were 2000 over lah. So it just print the top few thousand, and you can see that these are the most common. So meaning that the space occurred 6 million times. The comma occurred 495,000 times. Okay, so this one you did last week lah. So I won't label the fact. Let me comment that out so it doesn't flood the whole notebook. Okay, so now we'll be doing word embedding straight away, which is what the concept of last week was about, right? So you after your engrams was the thing, then after that word embeddings were the sort of like the breakthrough lah. So one of the libraries to work with word embeddings is GenSim lah. So if you look at GenSim, uh GenSim, this is some documentation. You can see it later. If you don't know how to install GenSim, you can read it lah. But it's just some documentation lah. Okay, not so important. Just know that GenSim is the thing that you can use the word embeddings for lah. Okay. Okay, so if you cannot install GemC, you need to do a pip install. You should be familiar with that. Go to your command prompt. If not, your Anaconda prompt. If you're using Jupyter locally, then you do a pip install. So when you install, as I said, once again, these are the tools that people have developed that we are using. There's no universal perfect tool. So in this case, we're just using the tools that they have and you just need to remember what are the libraries lah. So GenSim, there's some data path that you import that helps you to load data. There's a GenSim utils that helps you processing, and then the GenSim models, which is the AI models. Okay, looks like it's a typo here. AI models, and then yeah, and then OS. Okay, the OS one not needed. Yeah, to be commented out. Okay. So in this case, if you're familiar with object-oriented programming, sorry, lagging a bit, object-oriented programming, you can define a class lah. So a class, so I think this week one of my students asked me what is a class, because I think he or she forgot how it works really. Then I asked him to go and search it up. Then the response he came back was to tell me that, oh, a class is like something that you can store multiple functions in. Okay, yeah lah. Technically, you can call that a class lah. So in this case, this class, you just define it as class, and then with the semicolons inside, you define a function lah. So def, you define a function, iter, and then you have all this code. So in this case, whenever yeah, so in this case, this iter, for lack of a better way to explain, is that it will just run when you define the corpus lah. So when you call this class, this function will run, and then you want to save a data path here. So this is the end tokens that we saw that look like the TED talk, and then for each line in the open corpus path, you want to use a yield, the utils to process each line of code now. Okay, so yield is slightly different from return. You have never seen it before, or you need some refresher. Let me show it to you. Okay, so in this case, for example, I define my U function as for I in range 5 and then a UI lah. Okay, so if I do this, let me comment this out. If I do this, nothing really happens. It does not show anything. But for example, if I do the first U and I do a next, what's happening is that it will print out 0 lah. And then if I do second print with the next keyword, it will print out 1 lah, and then so on and so forth, 2 lah. So you can see that I have to call this function 5 times because the yield is like every time it reaches the yield, it will pause. And then if you run the next keyword or you run it again, it will do a second pass lah. So the long story short, is it here? No, okay. Long story short is that this U, every time you call the function, then it will start to process one line at a time lah. So in this case, it doesn't return the whole code, the whole document that's processed, but it return one line at a time every time it iterates lah. And that is good because it saves quite a lot of RAM and space lah. Okay, but not so important. I don't think you need to really know this. But it's just a back end for you to know that there's some processing of code from the end tokens library, end tokens text file lah. Okay, so in this case here, a GenSim model, there's some documentation here as well. The GenSim model, word to vec is you can see certain characteristics here lah. So this GenSim model, this work-to-vec model is an AI model. It helps to, as we mentioned before, lah, helps to do the word embeddings, which is the dimensional space, right? Which is the space, the very galaxy looking space that I showed the last time. I'll show you a refresher later. But this is the you can read documentation. If not, you can search Gen AI for help as well, lah. Okay. So word2vec is the word embedding model, lah. So sentences are the sentences that you want to give it. Then just how many times you want to run it and how many threads you want to run it and how many times you want to run it. Okay. Okay, so for example, I define my corpus as the class just now. So my corpus is the class here, and there's some pre-processing code. Okay, don't really need to know, just take note that there's some pre-processing code. And then I want to call the GenSim word2vec models based on the corpus lah, the sentences lah. You can ignore these definitions. The workers and the epochs can write any number, should be fine as well. Okay, so when the model comes out, so this model should be a word embedding the three-dimensional space. In case we need refresher, do I have it here? Okay, so I open this here. Uh, so if you remember last time we did this space last week, right? So if I click the word2vec, right, then you'll see the word2vec it's still initializing. It's like this three-dimensional map lah. So this is a visualization, but then in the code you can visualize it lah, but it's not so simple to visualize it lah. Okay, so imagine the example is Singapore. So when I click Singapore, Singapore, okay, maybe Singaporeans, okay. Then for example, Singaporeans here. Oh, there's no word connected to it. How come? Okay, let me try an easier one. Singapore. Okay, Singapore don't have also. Singapore. Okay, so in case of this Singapore, let me move around. How come I cannot move? Oh, I lost it. Sorry. Okay, never mind. Just pretend that Singapore is here. Like, it's so laggy. It's hard. Okay, but never mind. Just think about if I use this Kabul and then Kabul has a relationship to the all these words lah. Okay, this is a very bad example. Maybe I try university. I spell university wrong. University. I try university. University is here. You can see this line. It goes up. Universities here is related to faculty. It is faculty here and here. So there's a relationship lah. So you're storing something like this with the word2vec. Let me scrub again. You're storing this whole visualization. Since the model has already been trained, so the model has been trained with this map lah. So inside this map it will be stored as it'll be stored in this model here lah. Okay, yeah, it'll be stored at this model here lah. Okay, but in this case, oh sorry. In this case, you're training it with these sentences instead, yeah. But that case, so it will look something similar, but not exactly the same because you are using a different corpus of text. Okay. So in this case, you're training the model on the Kaggle input word embeddings and token.txt. So something like the TED Talk. And then now we are going to do some now we're going to do some exploratory data analysis on it, which means that we're going to look at what is the shape. Okay, so no points for guessing. It's 21731 rows by 100 columns lah. Okay, and then when we actually want to see it, you can see inside the model there are some indexes that if you see I can put here 0, right? It's the, and then with each word, right, there is a vector space that's allocated to it lah. So in this case here, you can see that the word the is represented by a bunch of numbers that look like this lah. So whenever somebody says vector space, what they mean is that words can be converted into numbers, but they don't necessarily have to be converted to a single number. They can be converted into a bunch of numbers lah. So in this case, the GenSim word2vec model has chose the to be 1, 2, 300. I think 100. Yeah, 1, 2, 3, 4. Yeah, should be 100. So this the okay, so sorry. What I'm trying to say is that there's 21731 words, and each word is represented by 100 values lah. So in this case, the is represented by these 100 values lah. And these 100 values are determined by the model that you use. So the word2vec GenSim model is some statistical way to do that lah. Okay, so don't need to know how it's done. Just know that it's a statistical method that gives it its number lah. Okay, so similar, same as the cosine similarity, same as all this kind of things. But actually, the word2vec model, the word embedding model is the best per se lah. Okay, so technically the stack that you should use when you are developing models is you can use ngrams as the features of the model, and then after that you just throw this uh throw this data into the word embeddings before you put into another model lah. Okay, but yes, but that we're still at the data pre-processing part lah. So in this case, I know there's a lot of terms you may not be very familiar with, but word embeddings is a good way to process data before you put into the model because it is able to break down each word into different ways. Yeah, so in this case, okay. Sorry, that's very verbose of me. But at the same time, when using the model, right, similar to how, for example, undergraduate, graduate, university is similar to each other. They have distances that are near to each other, right? Then in this case, when you want to pull out the most similar words to thought, in this case, the top 10 most similar words to thought. For example, if it says new could be 0.6% similarity lah. So how this similarity is done, it's not necessarily the cosine similarity, but it's more of the similarity that the word to vec uses lah. So it can be quite similar to the cosine similarity lah. So thought new is quite similar to each other. Thought realize is quite similar to each other. Thought think is quite similar to each other. Thought thinking similar lah. Okay, so the long way of me saying it is that you see we did so much matrices, right? But actually, a lot of libraries can really simplify all these things, lah. Okay, so somebody asked a question. How can how can a word translate to 100 dimensions? How can be translate? Yeah, to 100 dimensions. So it is possible lah. It's just there'll be there are many mathematical formulas to translate one word to a bunch of dimensions lah. But if you're asking how to visualize 100 dimensions is impossible. But how can one word just be translated into multiple dimensions is possible lah. So for example, maybe I can give you an example. So for example, if I say, let's think of let's think of the word living lah. Okay. In this case, you can make this into a one dimension, right? So living, you can just translate it to equals to zero lah. Or you can translate living to be, you can split it into two words, right? So I mean two words. You can split it into two tokens lah. Live equals to Okay, maybe living equals to one dimension. Then live equals to one dimension, and then ing equals to the second dimension. Okay, so you can see so on and so forth. It can be one dimension, two dimension, three dimension, four dimension, five dimension, six dimension. It can be this also. But this is not the maximum, right? Actually, you can do other things to split this up, right? So another way, another way for me to explain it, in this very famous neural net, this very famous model called the neural networks, you'll be able to break up things into multiple dimensions as an image. So for example, you see a plus can be one dimensional, it can be two dimensional, you can break it into up and down. But for example, if I do this, uh, sorry, if I do this, how many dimensions can this be actually? So the plus can become it can become nine dimensions lah. One dimension here, the zero, this nine dimension. But they can scale it up even more lah. So uh, yeah, can scale it up even more lah. So what you can do is think get the gist of what I mean. This is one way for me to express it lah. There are definitely other mathematical ways lah. Okay, so you can see this is also a plus, but it's one, two, three, four. Five. Five by five is 25 dimensions lah. So actually there are ways to split something into as many dimensions as possible. Hopefully I illustrated that. So yeah. Okay. In terms, okay. Because I was thinking similar, the other question is I'm thinking similar along the lines of machine learning's k-means clusters. Okay. But that can be done also, right? Wait, okay. Oh, you mean 100 clusters? Clusters and dimensions are not the same. I mean, they can be the same, but in this case, they are not the same. Okay, yeah. But that's just to let you know how to decompose things into smaller amounts, but it's quite tedious. So I try to not explain all these things if possible. But thank you. That's a good question to ask. Okay. At the same time, so where am I? Okay, so here, right, is the last part for today. Is it the last part for today? Let me see. Yeah, looks like it's the last part for today. So this is the last part that it's gonna fly over your head. So I mean, just prepare for this to fly over your head. But this is the part. The code is gonna fly over your head, but hopefully there is some way for you to pick up some useful points for today. So in this case, if you remember the term word analogy, uh, imagine that we are representing words as numbers now. So when you represent words as numbers, we can use words as equations lah. So meaning king minus man plus woman equals to queen, right? So if we are able to visualize words into numbers, right? So maybe king is 0, and then man is uh 1. Okay. And then woman is 2, and then queen is in this case -1 plus 2 will be 1, right? So oh, sorry, let me split it. So in this case, what's going to happen is that because in this vector space, imagine that you can have dimensions here, right? In this dimensional space, right, you can have a coordinate lah. So strictly speaking, if you're looking at just 3 dimensions, this undergraduate could be maybe if you draw lines like on x, y, and z axis, it can be like uh just for sake of imagination, it can be 1, 1, 1. So 1, 1, 1 is around here, the space like that lah. So think about it that if you can make anything to numbers, that's when the words can become numbers as well lah. Okay. So before we go on to the next part of the code is to talk about another form of word embeddings lah. So another form of word embeddings like similar to word2vec is this thing called the glove lah. Okay, so the glove stands for global vectors of word representation. So this is another word embedding. So today we go through some of the matrices, and the matrices were about the idea of how to make them into vectors, right? But then you know that the word embeddings also use vectors lah. So in this case, you're looking at the text glove 6B1050D. So it's trained on 6 billion tokens slash words, and then it's trained on it will represent each word with 50 dimensions lah. So maybe I'll pull up the glove. Glove, is it here? 50. Okay. So just for you to see is that you can see the is one of the words, and then the is there'll be 50 numbers that is associated with the. I'm not gonna count for you because it's very long. And then that, and then there is 50 numbers here that is associated with that. You probably can't see. It's just an on. There are a lot of words lah, a lot of numbers that yeah, too many numbers lah. Okay, too much numbers for a Friday night lah. Okay, so there is it's just ingesting all those words ah. So all this code here, long story short, because this is somewhat long, did I break it down? Or somewhat long, and I didn't break it down for individual parts. Is that the idea is that you want to convert all these words and numbers into their own parts lah. Okay, so in this case, what you'll see is that you want to create a vectors that is like a dictionary and there are words lah. Okay, so I mean in case this is quite flying over your head, it's because uh in the past now, of course, when I was learning AI as well, a lot of it was written by hand now. Okay, so that's why we're still explaining code. But in certain sense, maybe you need to learn small parts of the code with the concepts, and then in the future, maybe generative AI and coding development is going to be the future lah. But right now, we're still going to explain certain high level ideas for you to understand now. Okay. So just bear with me for the next 15 minutes, and I promise that it will be done within 15 minutes lah. Okay. So in terms of you are creating a dictionary, you're trying to put in the words, and then what is happening is that for each line inside the embeddings that you saw, the word with the 50 numbers, each word has 50 numbers, each word has 50 numbers, you're going to split each word lah. So each word, and then you're going to map each word with each vector lah. So nothing special now, like literally nothing special. You're just putting each word with its vector. You're just trying to split it up lah. Not necessary, in my opinion, not necessary to do, but it's because you will need to create other dictionaries lah. Okay, so in this case, what is happening is that there'll be two other dictionaries just for the long way and short way explaining it. So you don't need to always understand most of the encoding is that with all the words that you have, you want to get the index as well as the word definition. So you're gonna create the word and you're gonna pair it with the index. So you're gonna have a dictionary that has the word and the index, and you're gonna have a separate dictionary that has the index to word. Okay. So not very useful per se. Actually, all these things is just like processing for you to read all the words. That's all. It's for you to read all the words, okay? Yeah. So maybe just to make things very briefly short is that let's see if can I print out this final vector. Hope it doesn't crash. Yeah, wait, sorry, this gonna take some time. Okay. Oh, this bad. Hopefully it doesn't crash. Okay. Okay. Never mind. Let me just print this. Okay, so basically, there's just a conversion of the words to a vector space lah. So you're going to measure the vector space lah. So for example, the long story short, because this part not is important as the later part is that the idea is that whenever this you're running through the word and the vector space, there will be a word that will come out, right? And then the word is and then each word has its own index lah. So each word has its own index, but each word has its own vector space lah. Okay. And then in this case, this W, you want to throw away the word lah. You just want the vector space lah. Yeah. Which you'll use later lah. So it's just a bunch of vector spaces lah for you to take note. Okay. For you to take. Okay, wait. I need to run this again. If not, I think it will crash. Uh, Let me run this again. Okay. And then, long story short is that, as I said, a lot of statistics. Don't really need to know exactly what the statistics are, but then you sometimes want to do a normalization for each word vector lah. So every word has 50 vectors or has one vector or 50 numbers. You want to do something called a normalization, and what normalization is that in this case you want to convert it to a unit vector lah. But what I'm trying to tell you in simple terms is that you want to just simplify the numbers lah. You want to convert them. You just want to change the numbers in a different way lah. So in this case, after the normalization, you see the dot shape is that there are 400,000 words, and then there are 50 for each word. There are 50 columns lah. Yeah, so 50 dimensions lah. Okay, so now this is the most verbose part for today. This is the most verbose part for today. And this part is going to be the most complex lah. Yeah, so just bear with me. If see if I can hopefully help you understand this part now. Okay, so other than that, now what you're going to do is that you're going to evaluate whether in this you're going to evaluate a bunch of data that is king. For example, you'll be given four words: king, man, woman, and it's going to do this. It's going to do something like this as a formula, and it will try to predict the last word lah. Okay, so give you a sample of what I'm trying to say, which is if I took capital common countries dot text, okay, where is it? Capital common countries dot text. Okay, so a lot of this data you will see four words. Okay, so there'll be a formula here. So these three words will be like maybe this minus this plus this. Yeah, it will give you Iraq. Okay, so you can see this is a bunch of words like this. Let me pull up another example. Maybe I pull out 1 gram. I pull out 1 gram, which is maybe this amazingly minus amazing plus apparently gives you apparent gives you apparently lah. So amazing plus amazingly, uh, amazingly minus amazing plus cheerful will give you cheerfully lah. So amazingly, you minus the amazing for amazingly, you get ly. The ly plus cheerfully, you get plus cheerful, you get cheerfully lah. So you're gonna be doing essentially this for these evaluate vectors lah. Okay. So long story short, I won't breeze through most of these numbers, but I'll show you a subset of it first. I'll show you the output first lah. Okay. So basically these are all the file names, and as I show you some of the file names is four words and then the first three words, there'll be a formula that adds them, minus them together, and then it's trying to predict the last word. So that's it, all the words down here. Okay. So long story short, it will run through all the file names. So run through all the files and it will do the formula of I'll explain in detail. I'm just explaining the key highlights first. It will just do the formula of the second word. Uh, just treat it as the word with the index 2, which is the second word, minus the first word, and then plus the third word, and then it will give the prediction. And then with this prediction, you will compare between the real fourth word that is given inside the text. Okay, so just to be just to explain again is that so what it look like is amazingly minus amazing. Yeah, amazing minus amazing will give you ly, right? Plus become calmly. Okay, but you're gonna use the formula of that, which is this plus this minus this plus this, and the word to vec is gonna predict what is the next word. And if it predicts what's the next word, and then it's going to compare with this word to see if it's correct, right? Because AI model will do some form of prediction, but it may or may not be right, and you need to evaluate it. Okay, so generally that is the high level of that. But I will skip all this and come back later, but just explain to you. So in this case, what is going to happen is that there will be accuracy prediction of how well the model is doing. So in this case, the accuracy of the top one, the best prediction is that out of 506 rows of those four words, 401 predicted to be correct. So that's a 79% accuracy. Then in the just now I show you the first gram adjective. There are 992 of those questions, 992 of those rows of the four words, but the model predicted only 151 correct, so which is a 15% correct rate. Okay. Okay, so I'm just going to break up this idea a bit slowly. So do I need to okay, wait, actually I don't really need to explain these now. Okay, let me explain this part first. Okay, so what is happening is that I just simplified the code on the top into something more visual that you can understand and see. Okay, so don't worry, you will get this I was gonna say slide deck, but you'll get this Kaggle notebook also. So you can refer to it and you can try it on your own as well. And when you're doing your TMA or when you are revising, you can use this notebook as well. Okay, so I'm just going to use the sample data that I got from the capital, I think capital common country. So Athens, Greece, Baghdad. With these three words, we want the word to vec model that we trained on to predict Iraq. Okay, so similar, we want the Athens, Greek, Bangkok. With these three words, we want to predict Thailand. But yeah, but it seems to have quite high accuracy, right? You can see the capital common countries 80% accuracy correct. Yeah, quite interesting, right? Yeah. So basically what is happening is that in uh this temp data here, we are going to split it based on the new line. So at the end of all these characters, there is a backslash n that you cannot see. And then for each line, you want to split by space. So in this full data, you have Athens, Greece, and Baghdad, Iraq. Okay. And then when you do data, this doesn't look correct. Wait, let me print this. Let me run this. Sorry. Data, full data, temp data, X data, full data. Okay. Wait, Hmm. Okay, wait, this doesn't look. Let me check. Okay. In this case that I didn't add a code here. Oh, okay. Maybe it's not here. Yeah. Okay, so in this case, the main role is that it's just going to check if in this case, uh let me close this. Okay. The additional statement for this, for the full data is the same as the data because in this case, you're checking if the word it exists in the word to vec model. So word to ID, does it exist in the word to vec model? So this all just checks if it exists. So if it doesn't exist, then you have a problem with that line and don't use the line. So that's essentially what this line of code is saying. But just to let you know. It doesn't really do much. Okay. But then in this case now, what is happening is that same process as that function just now. What's happening is that you're gonna convert each word, uh, the data, each row for each data, and then for each word in each row. So for each individual element in each row, for each row, there will be words in every row. So for each row, you want to uh find the indices lah. So in this case, the word to ID, you want to put in the word to get the ID. So you're gonna convert it lah. So when I print indices, what you'll get is that you'll get 32642107 125 and 233 lah. So what this means is that imagine 32464 is Athens, right? So Athens is here. Then you go to the next array, right? 3264 again, because Athens is here. Then Athens is here, Athens is here. That's why 3264. But if you go to the last word, like Iraq, you go to Thailand and Beijing and Switzerland. That's why the ending words are different. Okay. And then after that, you need to do some transposing lah. So you can see that this array that you're looking at is like being rotated because it's doing a transpose. And because of the transpose, you will realize that you can do matrix calculations lah. So you forget your matrix calculations is like matrix calculations is like this row times this column, this row times this column, this row times this column, and that is one of the reasons why there's a transposition lah. Okay, not so important, but in case you need some explanation for that. Okay, and then after that, the last part is to be able to do some form of predictions lah. Okay, so because there are five questions here. There are five. One, two, three, four, five, right? So Athens, Greece, Baghdad. With this, you want to predict Iraq. With Athens, Greece, Bern, you want to predict Switzerland. So there are five questions here. So we want five predictions as well lah. So we want to have five predictions as well. We make it into we temp array first of five columns first lah. Okay, and what we want to do is that when the indices divide by 100, which is not so important, but I'll just gloss it. You don't need to really know. But what's happening is that when we want to test this model, we want to split this model into 100 questions at a time. But this is only five questions, so it will round up and you will just choose all the five questions lah. Yeah, so not so important. Let me move on. Okay, so now this is the one that is going to be quite confusing. So in this case, because this for loop is only going to run once lah, not so important. It's going to only run once. So for j in range of number iter will be just treat it as is one. It's going to run one round because there are only five questions. J will start with 0 if I'm not wrong. Okay, so long story short, the subset of NP range of 0 times something is 0, so it doesn't matter. It will start from A range 0, and then it will do a minimum of 0 plus 1 times the split size, which is okay, I didn't show you above, but it's split size 100 um, uh, versus the length of the index lah. So because j is 0 plus 1 times 100, so it's going to have a range of 100 comma length of index 1. So index 1 is only 5 questions, so in the end become A range 0, which is 0 here and 5 lah. So 0 and 5, okay? And then the important thing is the formula here, which is not so important, but you don't have to follow this format. Just to let you know that this is a formula that is defined in this question, but it doesn't really matter. Is that there's a prediction here. Using just treat it. I'm just going to make it simple. Just treat it as index 2 is the second word, and you go put it into the vector, the W to give you the vector. And then you're going to choose the second word's index. You're going to put it into to get the vector. And then you're going to plus the third word index, and then you're going to put into the vector. And then you're going to do a dot product, which is the normalized part that you have figured out just now lah. Okay, so because of that, then you're going to find the similarity, and with the similarity you are able to then compare lah. Okay, yeah, and then I will skip this part because this part is not necessary per se. Yeah, and then uh yeah, okay, yeah, this is the part that doesn't work. Let me put 100 because I deleted the split size. Okay. Okay, then after that, you are going to there's some returning of the predictions lah, and then you get the highest value. All this is just to let you know that what you're going to do is you're going to just figure out what the predictions are lah. So there are five questions and there are five answers for the predictions. Okay, there are five questions and there are five answers for the predictions over here lah. So right now, the last step is then to compare the predictions. These are numbers, but these numbers can be converted into words. These predictions you can compare with the actual indices number four, which is the actual value lah. Okay, so then when I run it, it says that two out of five of the predictions are correct lah. Two out of the five of the predictions are correct. So in this case, that is that part lah. Okay. So essentially, long story short, what is happening is that you have a word to vec model. What you're doing is that you're using the word to vec model to convert things from words to numbers and for numbers to words lah. So, but when you convert the words to numbers, they become numbers that you can do a formula on. In this case, would be the second word plus minus the first word, the third word minus the plus the third word, and then you get a number, right? So then this number you compare with the fourth words number and to see if it's correct lah. Essentially, that's the case lah. Okay, so then if we go back to the last part for today, which is when we look through uh, uh, there'll be a counting of all this. All there are a lot of questions here. The four word questions, three of the words. Then you predict the last word, right? There is a lot of it lah. And then you're supposed to count if they are semantically correct, the meaning is correct, syntactically correctly if the sentence is correct. So it's going to count all the correct sentences in different ways, and that's why for the first four files, they are for testing on the semantics lah for the first, and then the rest of the you're testing on the syntactic. Okay, so in this case, when it prints out the values of where for the evaluate vectors, when returning that, then it will show you the percentage accuracy of the correct prediction of the fourth word. But also it will sum up and say how many questions was predicted correctly based on the meaning, the syntax, and then the total accuracy. Okay, so I know that last part could have flew over your head, uh, but that's one use case lah. You will have done an AI model to predict from three words how you guess the fourth word lah. Okay, based on meaning lah. So that will conclude our word embeddings for today. That will conclude our word embeddings for today. I'll send you this notebook so you can digest it slowly. But my recommendation is to if you need any help for your TMA, then this would be a way to help you lah. So sorry, today is a bit more verbose, a bit more mathematical, but it will get easier lah in the future semesters lah. These are the most technical lah. Future seminars will be more fun. Okay. So with that, if you have any questions, I will still be here. If not, have a good Friday and have a good weekend. I will see you next week for another seminar. I'll see you next week for another seminar. So have a good night and have a good rest. Okay. If anybody has any questions. If not, yeah, if not, have a good night. Junhao is still here. Junhao asks, how does the ECA work for this module? So 1 week before, 1 month, sorry, one before the submission date, I can't remember. I think it's 4th April. It'll be released to you, and then, you just need to submit it with a Jupyter notebook, by the deadline. Yeah. Okay, good. If nobody has any questions, then have a good night. See you for next seminar.